Hello and welcome to our STEAM project number 6, based on the Raspberry Pi Pico and MicroPython. These lessons are designed for the somewhat experienced STEAM teacher. We call this intermediate level the Sherpa level. In our project number 6, we are going to build a distance measuring device based on the ultrasonic sensor HCSR04. My name is Peter. I am the founder of Educommando and a certified STEM instructor and course developer. The goal of today is to get familiar with a new component, the ultrasonic sensor HCSR04. Integrate this sensor in a project to measure the distance between objects. Learn how to program the HCSR04 in MicroPython, and the most important, to make sure that your class works as a team. Let's start by looking at this versatile and affordable sensor. You will notice the very recognizable eyes of the sensor. There is a transmitting unit, indicated with a small t, and there is a receiving unit, indicated with a small r. The sensor has 4 pins, a positive voltage pin, a ground pin, and in between there is the trigger pin and the echo pin. The theoretical working distance is between 2 centimeters and 400 centimeters, but the practical distance is often mentioned as between 2 centimeters and 80 centimeters. Keep this in mind, as you can give this as an experimental project to your class. You can use the whiteboard to explain the working principle to your students. In essence, this is quite simple and is actually very similar with the ultrasound navigation of bats. A sound is transmitted, and when it bounces against an object, that sound is returned to the receiving unit. The time difference between sending and receiving can be logged and used to calculate the distance. The speed of sound is 343 meters per second, or 1,235 kilometers an hour. Assume that you send a signal and that it takes 1 second to return. What would be the distance? Well, the distance would be 343 meters divided by 2, because you need to include the time that is needed to send the signal plus the time that it takes to come back. So if it would take 20 milliseconds or 0.2 seconds, how much would the distance be? Ask your class to calculate and give you the answer. If your ultrasonic sensor returns the sound signal in 0.2 seconds, then the distance it is measuring can be calculated using the following formula. So distance equals the speed of sound multiplied by the time taken divided by 2. So converting the time taken to seconds, we get the speed of sound being 343 meters per second, the time taken 0.02 seconds, and substituting the values, we get a distance of 3.44 meters. Therefore, your ultrasonic sensor is measuring an object that is 3.44 meters away from it. You can give your class a couple of exercises with different values so that they understand this formula really well. But now, it's building time. We will need the following components: the large breadboard with the Pico installed and the pinout reference card, the ultrasonic sensor, the box of preformed wires and the bundle of jumper cables, and the bed cardboard figure. First, we install the sensor on the breadboard. The 4 legs are connected as follows. The ground leg to one of the ground pins. The volted pin we connect to the pin VSYS or VSYS. This pin provides the 5 volt that the sensor needs. The trigger pin is connected to GPIO 2 and the echo pin is connected to GPIO 3. And we will use the REPL as our monitor to check the distances. Okay, now it's time to program. Open Thonny and create a new file. At the top of the program we can add some comments. And in MicroPython this is done by starting with the hashtag symbol. So hashtag file name, and we can call it distance hcsr02.py. Hashtag lesson number 6, Batman on the MicroPython, Raspberry Pi Pico, and for instance hashtag measuring the distance with the HC-SR04 Ultrasonic module. The first step is to import MicroPython libraries and modules and their classes. So for machine we will need pin, and this time we are going to import a complete library called uTime. Note that we use uTime, which is basically the same as the time module. Because we use 2 pins on the Pico, we are going to define them as the trigger pin equals the pin 2, and it is a pin out because we will send sound from it, and then the echo pin where we will receive sound from it, it's going to be pin number 3, and it's a pin in because we will receive from it. Now we go into our loop, our while true loop. So we first set the trigger pin value to 0. This is resetting the sensor to not sending anything. And then we also set the sleep. So from the library utype, we use the sleep class, and it's sleep underscore US5. The underscore US means that the following time indication is in microseconds. A microsecond is 1/1,000,000 of a second. Okay, so next is we are going to put the value of the trigger pin to 1, which means that we are activating the trigger pin to send a signal. And we will keep that state for 10 microseconds. So uTime dot sleep underscore US microseconds 10. And then we were going to put the value of the trigger pin back to 0 after the 10 microseconds, and so setting the value to 0 again. So that's for sending the signal. Now we need to read from the echo pin. So as long as the echo pin does not receive anything, or the value being equal to 0, the timer starts. And this is done with the command utime.ticks. So while the echo pin value is equal to 0, so the double equal sign, then we pass. Note that we need to use this pass or a null statement, or otherwise we will get a syntax error. So when there is nothing and we pass, otherwise we start the time and we use the start time equals utime.ticks in microseconds. So once the echo pin starts to receive a signal, the value is set to 1 and the end time is defined using the same ticks class. So while echo pin value is equal to 1, nothing happens, and we say end time equals utime.ticks _us. Now, with ticks, you cannot simply deduct the values, and it is recommended to use the command ticks _diff function with in between brackets the values end time and start time, and that will create the duration. So duration equals utime.ticks _diff, and then the two variables, your end time and your start time. Now that we have the duration, we can simply multiply this with the factor 0.0171 to arrive at centimeters. So the distance in centimeters equals duration multiplied by 0.0171. Because we want the result to appear in the REPL of Thonny, we simply use the print command and we say print in between brackets and hyphenated distance in centimeters and distance cm. And we can end with a delay of 1 second, so utime.sleep and in between brackets 1. Okay, let's run the program. You can see that the values are changing as we bring an object closer or further away from the sensor. If this all works perfectly with your class, a big congratulations. Now you can ask them to check till how far the sensor can produce meaningful results. You can also ask them, for instance, to check whether the distances that the sensor is showing are correct by using a ruler, and check with them if there is a difference. But what if for some groups in your class it doesn't work? Well, no panic. Do some logical fault finding. Were there any error messages in the REPL of Thonny? Did you select the right Raspberry and the right comms ports? Did you connect the components to the right GPIOs? Is the formula correct? Or are there any loose wires or legs? Maybe, just maybe, you are unlucky and one of the components is broken. That's it for lesson number 6. I hope you and your class really enjoyed it. In our lesson number 7, we are going to build a Ferris wheel based on a stepper motor and control the movement with a joystick. Looking forward to welcoming you again, and bye bye for now.